Let's look at the symmetries of a hexagon. There are 6 rotational symmetries, one of which leaves the hexagon unchanged, and additionally there are 6 reflectional symmetries. An important property of symmetries is that combining 2 of them always results in another symmetry. For example, first rotating by 60 degrees and then reflecting the hexagon results in the same symmetry as reflecting the hexagon along a different axis. This means that we have an operation that combines 2 symmetries into another symmetry. A structure with such an operation is called a group. We define a group to be a set with an operation which satisfies 4 properties. The first property is closure. We already saw that when composing 2 symmetries, you get another symmetry. More generally, combining any 2 elements in a group results in another element of the group. The next property is associativity. Here we require that the way elements are grouped in the composition doesn't matter, so the parentheses can be arranged without changing the outcome. Then we have the existence of an identity element. For instance, the 0-degree rotation does nothing, so we can compose this with any symmetry and it does not change the symmetry. In general, there should exist an element that, when combined with any other element, leaves it unchanged. The final property of a group is the existence of inverse elements. For every symmetry, there's another symmetry which reverses the first one. For every element in the group, there is another element such that their composition is the identity element. Using these 4 properties, we can derive many useful results about groups. For example, the identity element of a group is always unique. To prove this, assume that there are 2 identity elements. Then we compose them. By using that both elements are identity elements, we get that the product is equal to both identity elements. This implies that the identity element of a group is unique. We can also easily prove that the inverse of an element is unique. We denote this inverse of an element using an exponent of -1. We often drop the operation symbol when writing compositions. Let's look at some examples of groups. We already saw that the symmetries of a hexagon form a group. This is called the dihedral group D6. The identity element is a rotation of 0 degrees. The inverse of a rotation by 120 degrees is a rotation by -120 degrees. Every reflection is its own inverse. More generally, the dihedral group Dn describes the symmetries of a regular n-gon. It consists of n rotations and n reflections, giving it a total of 2n elements. On the natural numbers, we naturally have addition as an operation. This operation is associative and 0 is the identity element. But we do not have inverses, as negative numbers are not part of the natural numbers. Instead, we can look at the integers with addition, which form a group. This group does have the additional property of being abelian, which means that we can interchange 2 elements we are applying the operation to without changing the value. Another example of a group is the symmetric group. Here the elements are permutations of n elements. For instance, this is a permutation of 9 elements. We can always decompose a permutation in cycles. Another operation which allows us to form a group is matrix multiplication. Here's a set of invertible n times n matrices with entries in some field form a group. The identity element is a matrix with 1 on the diagonal and 0s elsewhere. When studying groups, it's often convenient to study subsets that also form groups under the same operation. Such subsets are called subgroups. A subset forms a subgroup if and only if the identity element is in the subset and the subset is closed under taking products and inverses. The smallest subgroup is always the subset with just the identity element. In the integers, the set of even integers form a subgroup, as the sum and difference of even integers is still even. More generally, for any integer n, all the multiples of n form a subgroup of the integers. To find more subgroups, we define powers of an element. For an element g, we define g to the power of n as g composed with itself n times. The zeroth power is the identity, and negative powers correspond to the inverse. The smallest subgroup contained in G consists of all its powers. For example, the subgroup generated by a 60-degree rotation contains all the rotation of a hexagon, while the subgroup generated by a 120-degree rotation consists of just 3 rotations. An important subgroup is the center of a group. This consists of all the elements that compute with every element in the group. A group is abelian if and only if its center is the entire group. For example, the center of the dihedral group D6 consists of just the identity element and the 180-degree rotation. An important result to understand the subgroups of a finite group is Lagrange theorem, which states that the number of elements in a subgroup divides the number of elements of the entire group. To illustrate this, consider a group as a set of points. A subgroup is a subset of these points. The rest of the elements can be grouped into sets of equal size, called cosets. The key fact is that the cosets partition the entire group into equal sized pieces. The total number of elements in the group is the product of the number of cosets and the size of the subgroup, proving Lagrange theorem. For example, in the dihedral group D6, which has 12 elements, possible subgroup sizes must divide 12. The subgroup of all rotations has 6 elements, and the subgroup consisting of the identity and a single reflection has 2 elements. If a group has a prime lemma p of elements, the only possible subgroups have size 1 and p, so only the identity element or the entire group. This means that any element other than the identity element generates the entire group, making it a cyclic group. A cyclic group is a group generated by a single element. A natural question to ask is whether the converse of Lagrange theorem also holds. So if some number divides the order of a group, is there a subgroup with that order? Generally, this is not the case. However, for example, when we are just looking at prime powers, this statement is true. To understand groups better, we need to know how different groups relate to each other. So suppose we have two groups G and H. We can look at maps from G to H which preserves the group structure, meaning the map F translates the operation of G into the operation of H. Such a map is called a group homomorphism. Let's look at a few examples. We know that the determinant is multiplicative, meaning it turns matrix multiplication into multiplication of numbers. This makes it a group homomorphism from the general linear group of matrices to the multiplicative group of a field. Another example is the exponentiation map, which converts addition into multiplication. Specifically, it defines a homomorphism from the complex numbers into addition to the non-zero complex numbers under multiplication. For any group, there's always a homomorphism from the integers into that group which map each element to the corresponding power of a given element. A bijective homomorphism is called an isomorphism. A function is bijective if every element in the target group corresponds to exactly one element from the original group. If there is an isomorphism between two groups, we say that they are isomorphic, and denote it like this. Isomorphic groups have the same number of elements and the same group structure, just with different labels for their elements. For instance, the exponentiation map from the real numbers under addition to the positive real numbers under multiplication is an isomorphism. This means that the two groups have the same structure, even though they appear different. An injective homomorphism is called a monomorphism. Injective means that different elements get mapped to different images. We can look at the images of a homomorphism and get that this is a subgroup of the codomain. By restricting the homomorphism to its image, we obtain a bijective map, meaning the domain is isomorphic to the image. In essence, a monomorphism embeds one group into a larger group. For example, all the symmetries of a triangle are also symmetries of a hexagon. So there is a monomorphism from the dihedral group D3 to D6. A surjective homomorphism is called an epimorphism. Surjective means that every element in the codomain has at least one pre-image in the domain. In this case, we can study the kernel, which is a set of all the elements in the domain that map to the identity element of the codomain. The kernel forms a subgroup and measures how much information is lost when passing from G to H. For example, consider the map from the integers to the multiplicative group of -1 and 1, which assigns each integer to its parity. Even numbers map to 1 and odd numbers map to -1. The kernel consists of all even integers. This means while individual integer values are lost in the mapping, the function retains information about whether a number is even or odd and how even and odd integers relate to each other. For example, the fact that odd plus odd is even is translated into -1 times -1 is +1. That odd plus even is odd is translated into -1 times 1 is -1. Now let's consider a general homomorphism between two groups. Every element in the kernel is mapped to the identity element. The remaining elements in the domain can be grouped into cosets, where elements in the same coset map to the same element in the codomain. The question is, can we define an operation on these cosets so that they themselves form a group and this map is again a group homomorphism? To answer this, let's take any subgroup of group and consider the set of its cosets. We attempt to define an operation by multiplying representatives of the cosets. The challenge is that different elements can represent the same coset, so the operation must yield the same result regardless of which representatives are chosen. A key observation is that if two elements belong to the same coset, the difference lies in the subgroup. Doing the same thing with the product and plugging n1 and n2 in, we get that this expression must be in the subgroup. This leads us to the concept of normal subgroups. A subgroup is normal if the inverse of G times n times G is always in the subgroup for all elements G in the group and n in the subgroup. For example, every subgroup of an abelian group is normal, and the kernel of every homomorphism is normal. The most important property of normal subgroups is that we can define a group structure on the cosets. The resulting group is called a quotient group. Together with a quotient group, we have a homomorphism called the canonical projection, which maps every element to its corresponding coset. The kernel is exactly the normal subgroup. Let's go back to the homomorphism. So we have found the operation which makes the left side into a group. Now we can restrict the map to its image, which makes this into an isomorphism. We get that the quotient group of G with the kernel is isomorphic to the image of F. This is also called the fundamental theorem on homomorphisms. Let's apply the theorem to our previous examples. For the determinant homomorphism, the kernel consists of matrices with determinant 1, which is known as a special linear group. The image covers the entire codomain, so we conclude that the quotient of the general linear group by the special linear group is isomorphic to the multiplicative group of the field. For the exponentiation map, the kernel is a set of all integer multiples of 2 pi times I, so we get this isomorphism. For the last homomorphism we considered, the image is a subgroup generated by G. If no power of G equals the identity, then the kernel is trivial and the subgroup is isomorphic to the integers. Otherwise, we let k be the smallest positive integer such that g to the power of k is equal to the identity element. Then the subgroup generated by g is isomorphic to the quotient of the integers by the multiples of k. This allows us to classify all cyclic groups. We get that every infinite cyclic group is isomorphic to the integers, and any finite cyclic group is isomorphic to some quotient of the integers. For example, the group of -1 and 1 under multiplication is isomorphic to the quotient of the integers by the even integers. More generally, the group of the roots of unity of order n is isomorphic to the quotient of the integers by the multiples of n. Now let's take a closer look at the quotient groups of integers. Consider the arithmetic of a clock. Adding 15 hours to 3 o'clock results in 6 o'clock. We express this as 18 being congruent to 6 modulo 12. The quotient group of integers modulo 12 captures the cyclic behavior. More generally, two integers are equivalent modulo n if the difference is a multiple of n. Another important type of homomorphism is an endomorphism, where the domain and codomain are the same group. A bijective endomorphism is called an automorphism. The set of all automorphisms of a group form another group under composition, known as the automorphism group. A special class of automorphisms are the inner automorphisms. Every element corresponds to one inner automorphism, and we have a homomorphism mapping every element to the corresponding inner automorphism. The identity element of the automorphism group is the identity map. The kernel is a set of all elements whose inner automorphism is the identity map. After rewriting this, we get that the kernel of the homomorphism is exactly the center of the group. So by the fundamental theorem of homomorphisms, we get that the quotient of G by the center is isomorphic to the group of all inner automorphisms. Say we want to color the edges of a hexagon with an equal number of green and red edges. By applying some symmetry of a hexagon to a coloring, we get a different coloring. We can do the same thing for all possible colorings and obtain a permutation of all the colorings. We say that the group D6 acts on the set of all colorings. This is an example of a group action. We define a group action of a group G on a set X to be a homomorphism from the group into the group of all permutations of the set X. So for every element in the group we have some permutation. Instead of writing pi where the index is a group element, we just write G times X. So the group element G acts on the set element X. Equivalently, we could define a group action to be a function taking an element from the group and an element from the set and giving another element from the set, such that the identity element leaves every element unchanged, and it doesn't matter whether we first let H act on X and then G act on the result, or we multiply G and H and let the product act on X. The second property looks like this in practice. Here we can first rotate and then reflect, or we just perform one reflection, which is a product of the other two symmetries. Let's look at some examples of group actions. The general linear group acts on the set of n-dimensional vectors by matrix vector multiplication. The symmetric group acts on the set of integers from 1 to n, where we just plug x into the permutation pi. Any group acts on itself by conjugation, where the result of G acts on X is G times X times the inverse of G. Let's go back to our colorings. We might want to know how many colorings there are. Using basic combinatorics, we get that there are in total 20 colorings. However, some colorings are very similar. For example, these two colorings only differ by a rotation, and these two only by a reflection. So we might be interested in the question of how many colorings there are up to an action of d6. To make this more precise, we look at the orbit of a coloring. This is a set of all the colorings which differ only by an action of the symmetry. So instead we could ask how many orbits there are. Let's make these definitions more formal. So consider a group acting on some set and an element x in that set. Then the orbit of x is the set of all elements that can be obtained by applying elements of G to x. To understand orbits better, let's look at the map, which maps each element to the corresponding element in the orbit. Then we can group together all the elements which get mapped to the same element. And we get the stabilizer subgroup and its cosets. Since we now have a bijection, this means that the index of the stabilizer subgroup is equal to the number of elements in the orbit. We define the stabilizer subgroup to be the set of all elements which don't change x. Then the result that the index of the stabilizer subgroup is equal to the number of elements in the orbit is called the Orbit-Stabilizer theorem. Using Lagrange theorem, we can also rewrite the equation like this. For example, when the symmetric group acts on the set of integers from 1 to n, the orbit of any element is the entire set, meaning this is a transitive action. Applying the Orbit-Stabilizer theorem, we find that the stabilizer of an element has size n-1 factorial. Since the remaining n-1 elements can be freely permutated, this confirms our intuition that the stabilizer of any element is isomorphic to the symmetric group of n-1 elements. When we look at all the possible colorings, we see that the orbits partition the set. It is now convenient to choose one representation element from each orbit. We can do the same thing for every group action. Since this union is disjoint, we get that the number of elements in X is the sum of the elements in the orbits. With the Orbit-Stabilizer theorem, we get the Orbit-Decomposition formula. A special role play the elements of X which are fixed by every group element. The stabilizer of these elements is the entire group, and the orbit is just that element. So we can collect all the terms in the sum corresponding to fixed elements to obtain this useful formula. Let's look at the example where a group acts on itself by conjugation. Here the orbits are called conjugacy classes. The stabilizers are called centralizers, and the set of all fixed elements is exactly the center of the group. Applying the Orbit-Decomposition formula, we derive the class equation of a group. Let's again turn to the question of how many orbits a group action has. We define the set of all orbits. We can express the number of elements in this set by summing the reciprocals of the number of elements in the orbit for each element in the set. Using the Orbit-Stabilizer theorem, we can express the sum using stabilizers. The sum of all the stabilizers is the same as the number of elements of this set, which in turn is equal to the sum of the number of fixed points a given group element has, where we are summing over all the group elements. Putting everything together, we obtain Burnside's lemma. Let's apply this to find the number of distinct colorings. There are 2 fixed points of a rotation by 120 degrees. For this reflection, there are 4 fixed points. In general, the number of fixed points for each symmetry is as follows. Now we can apply Burnside's lemma to find that up to an action of d6, there are in total 3 distinct colorings. The orbits look like this. We start with 2 definitions. For a prime P, a group is called a P-group if the order of the group is the power of the prime. A subgroup is called a Sylow P subgroup if its order is the largest power of P dividing the order of the group. In this chapter, we will study P-groups and how they appear as subgroups in general groups. Many of these results rely on group actions. Suppose a p-group acts on a finite set. Using the Orbit-Decomposition formula, we analyze the number of fixed points. For any non-fixed element, its stabilizer is a proper subgroup, meaning the orbit size is greater than 1 and divides the order of G, which is a prime power. Since the only divisors of a prime power are other prime powers, each orbit size is divisible by p. Reducing modulo p, we conclude that the number of elements in X is congruent to the number of fixed points modulo p. Applying this to conjugation, we see that the order of G is congruent to the order of its center modulo p. But G is a p-group. The left side is equivalent to 0. Since we know that the center of a group is non-empty, as the identity element is always in the center, we get that the order of the center is a multiple of p. Finally, this means that the center of a non-trivial finite p-group is non-trivial. Another result we could prove using this result is that if a prime p divides the order of a group, then there is some element in the group of order p, meaning that the order of the subgroup generated by this element is equal to p. The Sylow Theorems make statements about Sylow p subgroups inside a finite group. We have that there always exists a Sylow p subgroup we call p. For any p group, a conjugate of that subgroup is inside of p, and in particular, every two Sylow p subgroups are conjugates. And finally, the number of Sylow p subgroups divides M and is equivalent to 1 modulo p. If the number of Sylow p subgroups is equal to 1, the Sylow p subgroup must be normal. We can use these theorems to classify some small groups. We already know that every group whose order is prime is isomorphic to some quotient of the integers. Let's now look at groups whose order is the product of two different primes. Using the Sylow theorems, we get the following statements about the number of Sylow subgroups. Since p and q are primes, the only two divisors are 1 and the respective prime. Since p is smaller than q, p cannot be equal to 1 modulo q. So we know that nq is equal to 1. For np, the value can be either 1 or q. But if we assume that p does not divide q minus 1, we guarantee that np is also equal to 1. So both Sylow subgroups are normal and of prime order, so cyclic. We call the respective generators x and y. We can now form this product, which is called the commutator of x and y. On the one hand, by the normality of the subgroup generated by x, we get that this product is in the subgroup generated by x. On the other hand, we get that the product is in the subgroup generated by y. So it must be in the intersection. But the intersection is only the identity element. So the commutator is equal to the identity element, or equivalently x and y commute. We can apply this to see that the powers of the product of x and y is equal to the product of the respective powers. Using this, we can see that the order of the element of the product of x and y is equal to p times q. So the group G is generated by the product of x and y. This means that we have a cyclic group, which we already know is isomorphic to some quotient of the integers. For example, this implies that the only group of order 15 up to isomorphism is the integers modulo 15. We were able to do all of this since we assumed that both Sylow subgroups were normal. More generally, a finite group such that every subgroup is normal is called a nilpotent group. Since in an abelian group every subgroup is normal, an abelian group is nilpotent. To understand nilpotent groups, we define the direct product of two groups. Here we define an operation on the Cartesian product of the two groups by multiplying component-wise. If we have a nilpotent group and have all of its Sylow subgroups, then the group is isomorphic to the direct product of all its Sylow subgroups. For abelian groups, we can make an even stronger statement, as here the group is always isomorphic to some direct product of the integers modulo some prime powers. This is known as the fundamental theorem of finite abelian groups.